Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll take you through everything you need to know to get started with Amazon DynamoDB, AWS's fully managed NoSQL database service designed for high performance at any scale. We'll explore the core concepts like tables, items, and attributes, dive into capacity modes, scaling strategies, indexing, and data modeling. Let's get started. Amazon DynamoDB is a fully managed NoSQL database service designed for applications requiring low latency, high throughput access to data. It supports both key-value and document-based data models, making it versatile for a wide range of workloads. Built for seamless scalability, DynamoDB automatically distributes data across multiple partitions based on a hashed partition key, allowing it to handle millions of requests per second without manual sharding. By default, DynamoDB provides eventual consistency, but applications can opt for strongly consistent reads when needed. It also supports ACID transactions, enabling multi-item, multi-table operations with transactional guarantees. The service offers two pricing models: on-demand mode, which automatically scales throughput as needed, and provisioned capacity mode, where developers can allocate read and write capacity based on the workload to optimize costs. To enhance query flexibility, DynamoDB supports global secondary indexes, GSIs, and local secondary indexes, LSIs, allowing applications to efficiently retrieve data using alternative access patterns. Additionally, DynamoDB Streams capture real-time changes to table data, enabling event-driven architectures by integrating with AWS Lambda, Amazon Kinesis, or other services for change data capture, CDC, auditing, and analytics. Security is a core aspect of DynamoDB, with built-in AWS Identity and Access Management integration, encryption at rest using AWS KMS, VPC endpoints, and CloudTrail logging for auditability. It also complies with industry standards such as SOC, HIPAA, PCI DSS, and FedRAMP, making it suitable for highly regulated environments. Overall, DynamoDB is a powerful solution for applications requiring millisecond latency, automatic scaling, and seamless integration with AWS services, making it a preferred choice for high-performance workloads such as gaming, IoT, e-commerce, and real-time analytics. Here's a comparison of terminology between traditional relational databases, RDBMS, and Amazon DynamoDB, providing a clear mapping of equivalent concepts across both models. In Amazon DynamoDB, data is stored in tables, much like in traditional relational databases such as MySQL or PostgreSQL. However, DynamoDB tables are schemaless, meaning that while each table must define a primary key, the individual items, comparable to rows in an RDBMS, can have completely different sets of attributes. This offers significant flexibility in data modeling, allowing you to store varying structures within the same table without predefined schemas. Each item in DynamoDB is a discrete data entity composed of attributes, which are similar to columns in a relational model. But unlike relational databases where each row strictly adheres to a fixed column structure, DynamoDB allows items to include only the attributes they need. For instance, one item may contain fields for title, author, and publication date, while another item in the same table may include title, director, and runtime. To ensure uniqueness and efficient data distribution, DynamoDB uses a primary key. This key can either be a simple partition key, a single attribute, or a composite key made up of a partition key and a sort key. The partition key determines how the data is distributed across internal storage partitions, which is critical for scalability and performance. If a sort key is used, it allows multiple items with the same partition key to be stored together, ordered by the sort key, enabling efficient range queries. DynamoDB also supports indexes to extend querying capabilities. The Global Secondary Index, GSI, allows you to query data using an alternate partition key and sort key, independent of the base table's primary key. This is conceptually similar to non-clustered indexes in relational databases and supports eventually consistent reads. GSIs can be added or removed after the table is created, offering flexible access patterns as application needs evolve. On the other hand, a local secondary index, LSI, shares the same partition key as the base table, but uses a different sort key. It enables sorted access to data within a partition and maintains strong consistency with the base table. This is akin to a clustered index in relational systems, as the data layout aligns closely with the underlying table's partition key structure. In Amazon DynamoDB, tables are top-level entities and designed with schema flexibility, allowing each item, row, to have a different set of attributes. Unlike relational databases that enforce a predefined schema, DynamoDB's schema-less structure makes it ideal for applications that require dynamic and evolving data models. Every table in DynamoDB requires a primary key, which determines how data is stored and accessed. The primary key can be either a partition key, a single attribute, similar to a unique primary key in relational databases, or a composite key consisting of a partition key and a sort key. The partition key plays a crucial role in DynamoDB's scalability, as it determines how data is distributed across multiple storage nodes, while the sort key enables efficient querying and sorting of data within each partition. DynamoDB tables automatically scale and partition data across multiple nodes to handle varying workloads. When data is written, DynamoDB applies a hashing algorithm on the partition key to distribute records across storage partitions. This ensures that the workload is balanced, preventing performance bottlenecks and enabling the database to scale horizontally to accommodate millions of requests per second without manual intervention. DynamoDB stores data in a JSON-like format, allowing for flexible, semi-structured data modeling. Each item is represented as a collection of key-value pairs, where attributes can be scalars, strings, numbers, booleans, sets, lists, maps, or nested JSON structures. This flexibility enables efficient storage of hierarchical and complex data without requiring rigid table schemas. Let's begin by examining how data is typically modeled in a relational database. On the left side of the illustration, we see a traditional RDBMS design commonly used for managing a catalog of products. At the center is the products table, which holds general-purpose attributes shared across all product types. This table serves as the foundation, while more specific product details are separated out into dedicated tables: books, albums, and movies, each connected to the main table using foreign key relationships. These subtype tables contain attributes unique to each product category. For example, the books table may include attributes specific to books, while the albums table captures attributes relevant to musical releases, and the movies table holds attributes related to films. The model extends further in the case of albums through an additional level of normalization with a tracks table. This table stores track-specific metadata and links back to the albums table, forming a one-to-many relationship. While this normalized design promotes data integrity and reduces redundancy, it introduces complexity when querying. Retrieving a complete view of a single product may require multiple joins across several tables, which can increase latency, complicate application logic, and make the schema harder to evolve as the diversity of product types increases. Now, on the right side of the illustration, we see how the same product catalog could be modeled in a NoSQL database like DynamoDB. Instead of breaking up the data across multiple normalized tables, here we use a single table design that consolidates all product information, regardless of type, into individual items within one table. The table uses a composite primary key, where the partition key is the product type, such as book, album, or movie, and the sort key is the product ID. This allows for logical grouping of items by type while maintaining uniqueness across all products. What's most interesting about this design is that each product's metadata, whether it's ISBN and publisher for a book, or artist and track list for an album, is stored directly within the same item as the core product attributes. Even the tracks for an album can be embedded as a list of nested documents within the album item itself. This is possible because DynamoDB supports a flexible schema. Each item can have a different set of attributes, tailored specifically to the product type it represents. By flattening the data and storing it in a denormalized format, this design is optimized for high-performance single-table queries. You can fetch a complete product record, including all its details, in one request with no joins, which is a major advantage for read-heavy, latency-sensitive applications. Amazon DynamoDB supports three main categories of data types: scalar types, set types, and document types, each designed to handle different types of data efficiently. Scalar types are the most fundamental data types in DynamoDB. representing single indivisible values for an attribute. They form the building blocks of most data models and are used extensively across items. String. This type stores text data encoded in UTF-8. Each string attribute can be up to 400 kilobytes in size, making it suitable for storing names, descriptions, identifiers, or even JSON blobs when needed. String attributes can be sorted lexicographically, which is particularly useful when used as part of a sort key in composite primary keys. Number. Although stored as strings internally to maintain precision, numbers are treated numerically for comparisons, filtering, and mathematical operations. This type supports both integers and floating point values, making it versatile for representing quantities, prices, timestamps, and any numeric calculations. Boolean. The Boolean type holds either a true or false value. It's ideal for status indicators such as flags, feature toggles, or conditions that control application logic, like whether a product is in stock or a user is active. Binary. This type is used to store raw binary data, such as images, encrypted content, serialized objects, or multimedia. Since DynamoDB is schemaless, binary data can be stored and retrieved easily as long as it conforms to base64 encoding during API interactions. Null. Unlike simply omitting a field, setting an attribute to null explicitly indicates that the value is intentionally undefined or missing. This can be useful in modeling optional fields or when a placeholder is needed to preserve schema expectations in downstream applications. These scalar types provide flexibility and control over how individual attributes are stored and retrieved in DynamoDB. Set types in DynamoDB are designed to store collections of unique values, offering a convenient and efficient way to represent distinct elements within a single attribute. Unlike lists, sets do not preserve order and do not allow duplicates, which makes them ideal for scenarios where uniqueness is essential. String set. This type stores an unordered collection of unique strings. It's commonly used for attributes such as tags, categories, or roles. Any scenario where a single item may be associated with multiple string identifiers that should not repeat. Number set. This stores a unique group of numeric values, making it useful for representing things like product IDs, user scores, or feature flags represented as numbers. DynamoDB ensures that duplicate numbers are automatically removed, simplifying application logic and reducing the risk of data anomalies. Binary set. The binary set is designed to hold unique binary objects, such as file hashes, security tokens, or encoded data blobs. This is particularly useful in applications dealing with secure or hashed content, ensuring that duplicates do not take up extra space or create inconsistencies. Set types are especially powerful when you need to manage distinct groupings of values while keeping your data clean and concise. They are a natural fit for modeling many-to-one relationships or performing set-based operations at the application layer without needing additional tables or complex joins. DynamoDB's document types are ideal for applications that deal with nested, hierarchical, or semi-structured data. These types allow developers to model complex relationships directly within a single item, eliminating the need for multiple tables or relational joins. The two primary document types are list and map, both of which provide flexible, JSON-like data structures. List. This type stores an ordered collection of elements, much like an array in JSON. Each element in the list can be a scalar, such as a string or number, a set, or even another list or map, enabling deep nesting. Lists are ideal for use cases like representing a sequence of events, ordered tags, or track listings in an album. Their ordered nature ensures that position is preserved, which can be important for workflows or ordered data representation. Map. The map type functions like a dictionary or JSON object, storing key value pairs where the keys are strings and the values can be any valid DynamoDB data type, including other maps or lists. This makes it incredibly powerful for capturing structured metadata, configuration settings, user profiles, or any data that varies in structure across items. One of the most powerful features of document types is that they can be arbitrarily nested. A map can contain lists, which in turn contain maps, and so on. This mirrors the structure of JSON, allowing applications to serialize and deserialize complex objects easily. Because DynamoDB is schemaless at the item level, document types allow each item to have a custom structure, tailored to the specific needs of the application. This flexibility makes it especially well suited for use cases like content management systems, catalogs, IoT data, or any domain where the shape of data may evolve over time. By leveraging document types, developers can simplify their data modeling, reduce the number of queries required to retrieve nested information, and build applications that are both agile and scalable. In Amazon DynamoDB, applications can choose between eventual consistency and strong consistency for read operations, each offering different trade-offs in terms of performance, availability, and accuracy. With eventual consistency, read requests may return stale data if recent writes have not fully propagated across all replicas. This approach prioritizes high availability and performance, as reads can be served from multiple replicas without waiting for full synchronization. Since eventual consistency allows DynamoDB to distribute workload efficiently, it is well suited for high-performance applications where slightly outdated data is acceptable, such as caching, recommendation engines, and analytics. Additionally, eventual consistency is the only option available for global tables, ensuring that data replication across AWS regions remains scalable and efficient. In contrast, strongly consistent reads always return the most recent committed write, ensuring that applications retrieve up-to-date information. However, this comes at a cost. Strong consistency requires higher latency, as DynamoDB must coordinate across replicas before serving the latest data. Strongly consistent reads also consume twice the read capacity units, RCUs, compared to eventually consistent reads, making them a more resource-intensive option. Moreover, strong consistency is only available within a single AWS region and cannot be used for global tables. Another important consideration is how global secondary indexes GS handle consistency. GSIs in DynamoDB are eventually consistent by default, meaning index updates may lag behind the base table. Applications requiring strict consistency must design queries accordingly, as GSIs do not support strong consistency. Ultimately, the choice between eventual and strong consistency depends on the application's needs. Eventual consistency is ideal for high-performance distributed workloads, while strong consistency is necessary for real-time accuracy in use cases such as financial transactions, inventory management, or user profile updates. Transactional operations provide strong consistency for both reads and writes. This means that the data returned by a transactional read will always reflect the most recent committed writes. The transactional writes will also be guaranteed to be applied consistently across the system, meaning no partial writes will occur. If one operation fails, the entire transaction is rolled back, ensuring data integrity. Why to use transactional consistency? Transactional consistency ensures that data modifications within a transaction are isolated from other transactions and consistent with each other. For instance, if a transaction involves updating two related items, the system guarantees that both updates are applied together, or neither is, even if the operation spans multiple tables or partitions. This consistency model provides strong isolation between transactions, preventing issues like dirty reads or lost updates that can occur in non-transactional systems. However, transactional consistency does introduce overhead compared to standard operations due to the additional guarantees provided, such as locking and coordination across multiple items or tables. When to use transactional consistency? Transactional consistency is most useful when you need to perform complex, multi-step operations where consistency is critical across different items or tables. Some common use cases include financial transactions, where you need to ensure funds are debited from one account and credited to another, with no partial updates. Inventory management, where stock levels across multiple warehouses need to be updated atomically. Order processing, where multiple items in an order need to be updated simultaneously to reflect the correct order status, inventory, and shipping information. There are a couple of limitations of transactional consistency in Amazon DynamoDB: size and item limits. Each transaction can include up to 25 items and can be up to 4 megabytes of total data. This means that large datasets or high-volume write operations may require splitting the transaction into multiple smaller ones. Throughput constraints. Transactional operations are more resource-intensive than regular operations. This can result in higher read and write capacity unit consumption, which may impact performance, especially for high-throughput applications. Also, transactions have stricter latency requirements compared to standard operations. In provisioned capacity mode, DynamoDB allows you to define in advance the number of read capacity units, RCUs, and write capacity units, WCUs, that a table or index should support. This means you're explicitly setting the throughput the system is expected to handle, and your build based on the capacity provisioned, whether or not it is fully consumed. This model is particularly advantageous when you have a good understanding of your application's workload patterns and can estimate traffic volume ahead of time. To help balance performance and cost efficiency, auto-scaling can be enabled within provisioned mode. This feature monitors the utilization of your table and automatically increases or decreases the provisioned throughput based on defined thresholds and actual usage. It ensures that your application remains performant during sudden traffic spikes while scaling down during low activity periods to save costs. Despite auto-scaling, you still have fine-grained control over minimum and maximum capacity settings, providing predictability and cost management. One of the major benefits of this mode is cost predictability. Because you allocate capacity up front, your monthly billing remains stable and consistent, making it easier to budget for DynamoDB usage, an important consideration for production systems with strict financial oversight. Provisioned capacity mode is best suited for workloads with consistent or predictable access patterns, such as internal enterprise systems, scheduled batch jobs, or well-modeled APIs with steady traffic. However, it's important to note that this mode comes with certain scaling limitations. There's a finite rate at which provisioned capacity can be adjusted per minute, and if your application exceeds the configured limits, DynamoDB will throttle requests, leading to increased latencies or failed operations until the demand subsides, or the provisioned limits are raised. In on-demand capacity mode, DynamoDB takes a fully automated approach to scaling. It dynamically adjusts throughput in real time to meet your application's demands, without requiring any manual configuration or capacity planning. As traffic fluctuates, whether it surges or drops, DynamoDB seamlessly scales to match it, ensuring consistent performance and eliminating the risk of throttling due to under-provisioning. This model is particularly well suited for applications with unpredictable or spiky workloads, where traffic patterns are hard to forecast or can vary widely throughout the day. Because you're billed only for the actual read and write requests made, on-demand offers strong cost efficiency for workloads that aren't consistently high in volume. This makes it ideal for new applications, prototypes, startups, or any scenario where traffic patterns are still evolving or difficult to predict. One of the biggest advantages of on-demand is the elimination of capacity planning. Developers don't need to estimate future throughput or monitor scaling thresholds. DynamoDB handles it all behind the scenes. This makes it a hands-off solution, perfect for teams that prefer operational simplicity and need the flexibility to grow or shrink with minimal overhead. However, for applications with steady and predictable workloads, the cost structure of on-demand can sometimes be less economical than provisioned capacity. Since you pay per request, high-volume steady-state workloads might accrue higher charges compared to a well-tuned provisioned setup. In Amazon DynamoDB, a local secondary index, LSI, provides an alternative way to query and sort data within the same partition key while using a different sort key. This makes LSIs particularly useful when multiple query patterns are needed for the same set of partition data. LSIs must share the same partition key as the base table, but they allow sorting and filtering based on a different attribute. This enables efficient retrieval of data using alternate sorting criteria, such as retrieving a user's most recent transactions or filtering records based on timestamps. However, LSIs must be defined at the time of table creation and cannot be modified later, making them less flexible. One of the advantages of LSIs is that they support strongly consistent reads, ensuring that queries on an LSI always return the most up-to-date data. This is in contrast to GSIs, which only offer eventual consistency. However, LSIs share the provisioned throughput of the base table, meaning they consume the same read and write capacity units, RCUs, WCUs. As a result, heavy query loads on an LSI can impact the overall performance of the table if not properly managed. Since LSIs maintain their own copies of indexed attributes, they also increase storage costs, as every indexed item takes up additional space in DynamoDB. Despite this, LSIs are a powerful tool for applications that require multiple query patterns within the same partition, such as sorting user activity logs by date, retrieving order histories by status, or filtering event records by priority. When designed correctly, LSIs can significantly improve query efficiency while keeping data retrieval fast and scalable. In our illustration of local secondary indexes, LSIs, in DynamoDB, we begin with a base table that uses A1 as the partition key and A2 as the sort key. This combination forms the primary key for the table. When LSIs are created, the partition key, A1, remains unchanged across all indexes, preserving the partitioning structure of the base table. However, each LSI introduces a different sort key to enable alternate query patterns within the same partition. In the first LSI, we define A3 as the alternate sort key, and we include A2 as a projected attribute. Since A2 is part of the base table's primary key, it is automatically projected into all LSIs, even if not explicitly requested. The second LSI is built using A4 as the sort key, and this time we project A2 and A3 as additional attributes. This allows queries within the same partition, A1, to be ordered and filtered based on A4, while still being able to access A2 and A3 efficiently without consulting the base table. The third LSI uses A5 as the sort key and projects all attributes from the base table. This effectively mirrors the full item structure, but orders and indexes it based on the new A5 attribute. This is particularly useful when you want to support complex queries that require sorting or filtering on attributes not originally part of the base sort key. A key point to note is that because A2 is part of the original primary key, it will always be present in the LSI schema. LSIs are thus ideal for scenarios where you want to enable alternative sorting or filtering within the same partition key context, without changing the overall partitioning logic of your table. A global secondary index, GSI, in DynamoDB offers the flexibility to query your data using an entirely different partition key and sort key than those defined in your base table. This makes GSIs incredibly powerful for enabling alternative access patterns and efficiently retrieving data that spans multiple partitions, which isn't possible with local secondary indexes. Unlike LSIs, GSIs are completely decoupled from the base table's primary key structure. They can have their own partition key and sort key, allowing for a wider range of query operations across the dataset. This means you can design indexes that serve specific application needs without being constrained by the base table schema. One important characteristic of GSIs is that they support only eventually consistent reads, which allows them to scale efficiently, though with a slight lag in reflecting updates from the base table. Also, GSI updates are asynchronous, meaning that changes to the base table are propagated to the GSI in the background. This ensures non-blocking performance, but requires consideration for potential staleness in real-time scenarios. From a capacity standpoint, GSIs operate independently from the base table. In provisioned mode, you allocate separate read and write capacity units for each GSI, and in on-demand mode, they are billed separately based on their own activity. Indexed attributes are fully maintained by the GSI, ensuring that all necessary data for query and projection is available within the index itself. A key advantage of GSIs is their flexibility. They can be created or deleted at any point after the table is created, allowing your data model to evolve over time without requiring disruptive changes to the base table. Additionally, DynamoDB supports up to 20 GSIs per table, a soft limit that can be increased. And unlike LSIs, there's no size restriction on the items that can be indexed, making them suitable for large-scale, dynamic use cases. In this illustration, we're looking at how global secondary indexes, GSIs, work in DynamoDB by using three examples built on top of an original table. The base table uses A1 as the partition key and A2 as the sort key. This defines the primary way data is organized and accessed in the table. To support alternative query patterns, 3 GSIs have been created, each with a different key structure and projected attributes. The first GSI uses A3 as its partition key and includes A1, the original table's partition key, as an additional projected attribute. This setup allows you to efficiently query items based on A3, even though it's not part of the base table's primary key. The second GSI takes it a step further by using A5 as the partition key and A4 as the sort key. In addition to this alternate key structure, it projects 2 additional attributes, A1 and A3, to make queries more meaningful and complete. The third GSI is even more comprehensive. It uses A4 as the partition key and A5 as the sort key and projects all attributes from the base table. This effectively provides a fully flexible index that can serve a wide variety of access patterns. Together, these GSIs demonstrate how you can use alternate partition and sort keys to reshape your access to data without duplicating the table. Since GSIs do not have to follow the key schema of the base table and can project only the needed attributes, they offer a powerful way to support multiple query scenarios while maintaining a single source of truth. Both local secondary indexes, LSI, and global secondary indexes, GSI, in DynamoDB enhance querying capabilities, but they serve different purposes. When deciding between local secondary indexes, LSI, and global secondary indexes, GSI, in DynamoDB, the right choice depends on the data access patterns, consistency requirements, and cost considerations. If your application frequently needs to retrieve and sort data using different criteria within the same partition key, then a local secondary index, LSI, is the appropriate solution. LSIs provide alternate sort key options while keeping the partition key fixed, allowing you to efficiently run queries that vary based on how items are ordered within that partition. A key advantage of LSIs is that they support strongly consistent reads, meaning the data returned is always up to date with the base table. This makes LSIs ideal for use cases that require real-time accuracy and consistency. However, there are a few important limitations. LSIs must be defined at the time of table creation, and you cannot add them later as your data model evolves. Additionally, LSIs share read and write capacity with the base table, so heavy usage of LSIs could impact the overall performance of your table if not carefully managed. This shared throughput model makes provisioning and capacity planning a critical consideration when using LSIs in write-heavy applications. In contrast to LSIs, if your application requires access to data using completely different partition keys, essentially alternate ways to organize and retrieve your data across the entire dataset, then a global secondary index, GSI, is the better choice. GSIs enable queries based on attributes that are entirely independent of the base table's primary key, giving you the flexibility to support diverse and changing access patterns. This makes GSIs especially powerful in applications where data needs to be retrieved by multiple different fields. A major advantage of GSIs is that they can be created or removed at any time, allowing your data model to evolve as business needs change without needing to recreate the entire table. This dynamic flexibility is ideal for agile environments, or when requirements are uncertain at the outset. However, GSIs come with trade-offs. Since they operate asynchronously, updates to the base table are not immediately reflected in the GSI. As a result, eventually consistent reads are the default for GSIs, which means there may be a short delay before the most recent changes are visible in queries against the index. While this is acceptable for many applications, it's important to consider if real-time accuracy is critical. Also, GSIs have independent capacity from the base table, so they require separate provisioning or are billed independently under on-demand mode. When deciding between LSI and GSI, it's important to evaluate the characteristics of your query patterns, consistency expectations, and scalability requirements. If your application demands real-time updates and strongly consistent reads within the same partition, an LSI is more appropriate. However, if you need to query data using a different partition key, spanning across multiple partitions, a GSI provides the flexibility and adaptability to support evolving access patterns and business use cases. Autoscaling in Amazon DynamoDB ensures that database performance remains efficient by dynamically adjusting read and write capacity in response to changing workloads. Instead of manually provisioning read capacity units, RCUs, and write capacity units, WCUs, autoscaling helps maintain optimal performance while balancing cost and resource utilization. At its core, DynamoDB autoscaling operates based on a target utilization percentage, typically set around 70% of the allocated capacity. When actual usage approaches or exceeds this threshold, autoscaling increases capacity, and when demand decreases, it reduces capacity, preventing overprovisioning and unnecessary costs. This mechanism relies on Amazon CloudWatch alarms and scaling policies, which continuously monitor throughput metrics to make real-time adjustments. One important consideration is that global secondary indexes, GSIs, require independent scaling policies. Unlike local secondary indexes, LSIs, which share throughput with the base table, GSIs operate separately and must have their own auto-scaling settings to ensure efficient performance. Auto-scaling behaves differently based on the capacity mode chosen for the table. In provisioned capacity mode, read and write throughput is explicitly set, and auto-scaling dynamically adjusts it within defined limits. However, in on-demand mode, DynamoDB automatically scales without requiring predefined capacity settings, making it an ideal choice for unpredictable workloads. It is important to note that auto-scaling does not happen instantly. Since it relies on CloudWatch metrics, there is a response delay, typically a few minutes, before scaling changes take effect. Additionally, cooldown periods ensure that frequent adjustments do not lead to excessive scaling fluctuations. By properly tuning auto-scaling settings, such as setting minimum and maximum capacity limits, adjusting target utilization percentages, and monitoring workload patterns, organizations can prevent throttling during traffic spikes while avoiding unnecessary costs. Optimizing these configurations ensures that DynamoDB can efficiently handle fluctuating demand while maintaining high availability and cost efficiency. Amazon DynamoDB Streams provide a powerful mechanism for capturing real-time changes in a table, allowing applications to track inserts, updates, and deletions as they occur. This feature enables change data capture, CDC, by recording a time-ordered sequence of item-level modifications, making it useful for event-driven applications, real-time analytics, and cross-system synchronization. DynamoDB Streams maintain records for a 24-hour retention period, ensuring that changes are available for processing without accumulating excessive storage costs. This temporary but efficient storage allows applications to consume updates in near real time while keeping resource consumption minimal. To provide flexibility in how changes are recorded, DynamoDB Streams offer 4 different stream view types. The keys-only mode captures just the primary keys of modified items, while the new image and old image modes store the complete item state before or after a modification. For a complete audit trail, the new and old images mode captures both pre-update and post-update states, offering comprehensive visibility into data changes. One of the most common use cases for DynamoDB Streams is event-driven processing using AWS Lambda. When a change occurs in a table, a Lambda function can be triggered asynchronously, allowing applications to execute real-time workflows, such as sending notifications, synchronizing data across systems, or updating derived data sets. For applications that require strict ordering, DynamoDB Streams guarantee ordered event delivery within each partition key. This ensures that all changes related to a specific item are processed in the exact sequence they occurred, making it particularly valuable for applications that depend on sequential data consistency. DynamoDB Global Tables enable the creation of fully replicated tables across multiple AWS regions, offering businesses a powerful solution for low-latency, globally distributed applications. By automatically replicating data across regions, global tables ensure that users can access data close to their location, providing quick response times regardless of geographical distance. One of the standout features of global tables is their ability to synchronize data across regions in near real time. Any change made in one region is automatically propagated to other regions, ensuring that the database remains consistent and up-to-date globally. This feature is crucial for applications that require high availability and resilience, especially in scenarios where uptime is a critical concern. Importantly, strong consistency is maintained for reads within the same region, ensuring that data is always accurate and up to date when accessed locally. However, cross-region reads may be eventually consistent, meaning that there may be a slight delay in replicating the latest changes across regions. The best part is that global tables are fully managed by AWS, meaning developers don't need to worry about the complexities of data replication or conflict resolution. AWS takes care of automatically managing these processes, allowing teams to focus on application logic rather than infrastructure maintenance. However, when concurrent writes happen in multiple regions, DynamoDB resolves potential conflicts using a last writer wins strategy. The most recent write, based on the timestamp, is accepted, ensuring that the data remains consistent even if conflicts occur across regions. While this simplifies the synchronization process, it's essential for developers to design applications that minimize simultaneous writes in different regions to avoid potential issues. To accommodate different workloads, DynamoDB global tables support both provisioned capacity and on-demand capacity modes. This flexibility allows businesses to scale their databases based on usage, whether they prefer to control throughput manually or rely on automatic scaling to handle traffic fluctuations. Amazon DynamoDB provides robust backup and restore capabilities to ensure data durability, compliance, and disaster recovery. These features allow businesses to safeguard their data against accidental deletions, corruption, or system failures while maintaining high availability and performance. DynamoDB supports on-demand backups, enabling users to create full table snapshots at any time. These backups do not impact table performance and can be retained indefinitely for compliance or archival purposes. For organizations needing continuous protection, point-in-time recovery (PACR) offers an automated backup mechanism that enables restoring a table to any point within the last 35 days. This is particularly useful in scenarios where accidental deletions or data corruption need to be reversed. One of the key advantages of DynamoDB's backup system is that it operates asynchronously in the background, ensuring zero impact on read and write performance. However, while full table backups and restores are supported, granular restores of individual items or specific attributes are not possible. To retrieve specific data, users must restore the entire table and manually extract the necessary records. For enhanced disaster recovery and cross-region resilience, DynamoDB supports cross-region backups, allowing backups to be copied to different AWS regions. This ensures that critical data remains available even in the event of a regional outage. Additionally, all backups are automatically encrypted using AWS Key Management Service, KMS, providing security and compliance with industry regulations. Restoring a backup creates a new table rather than overwriting an existing one. This means applications must be manually redirected to the restored table, and certain settings such as indexes and auto-scaling configurations need to be reconfigured after restoration. From a cost perspective, backup storage is billed separately based on the size of the backed up data, and PyTorch incurs additional charges for continuous backups. However, restoring data itself is free, with costs only applying to the storage and provisioned capacity of the newly restored table. By leveraging a combination of on-demand backups, PITR, and cross-region replication, organizations can build a resilient and cost-effective backup strategy that meets both compliance and operational recovery needs. Monitoring is a critical aspect of managing DynamoDB effectively, and AWS provides powerful tools to support this. DynamoDB integrates seamlessly with Amazon CloudWatch, offering detailed performance metrics such as read and write throughput and request latency. These metrics help identify how well your application is utilizing the table and whether it's meeting performance expectations. By closely observing the consumed versus provisioned or on-demand capacity, you can fine-tune query patterns and ensure you're not over or underutilizing your resources. CloudWatch also plays a vital role in highlighting instances where read or write operations exceed allocated limits, leading to throttling. Identifying such patterns early can help you address inefficiencies in your access strategy or adjust capacity settings proactively. When DynamoDB streams are enabled, monitoring becomes even more important to ensure that stream consumers are keeping up with the data changes in real time. Lag in stream processing can affect downstream applications that rely on timely updates. Additionally, AWS CloudTrail can be used to log all DynamoDB API calls, providing a comprehensive audit trail. This is invaluable for troubleshooting issues, conducting security audits, and ensuring compliance in production environments. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.